For example, I show these two figures again about this orthogonal carding because orthogonal carding is one. Okay, so you need to be very, very clear about the shear angle, wrinkle angle, clearance angle, or called relief angle. Also, this is T0, and T0 stands for this is the uncolored tube thickness, and TC is standing for the tube thickness of velocity. And then this one tube formation, and we use the sine function that we have learned in the trigonometry, and so to relate is the cutting force V along with the tube cutting velocity, cutting speed V, and the VC is the tube speed, and VS is the shear speed, and shearing speed on the shear plane. Here's the gamma. We also have a gamma. Gamma is the speed rate along this shear plane. So please write down this. So this is the beta alpha. We have alpha is a rectangle. The beta is defined as this. Right. So here is R is the resultant force. Suppose we have this is the current speed. So we have the reaction force. If we have the cutting speed, that means that and your tool is going to cut this workpiece. So based on Newton's third law, and so with the workpiece, and we'll give the reaction. So one reaction is Fn is along. This is the perpendicular. Is perpendicular to the shear plane. This Fn perpendicular to the shear plane. So we also have this Fs. Fs is the shear force along this is the shear plane. So as long as these two guys they are perpendicular, they're orthogonal, that'll be okay, right? So here is the resultant. This is the resultant force. We know if we apply the external load, and so definitely, so this is the workpiece, and will give us reaction force. Reaction force can be decomposed into Fn and Fs. So we suppose this is the resultant force. So here is another angle I want to emphasize. So this is beta. So this is beta. Beta is defined as the tangent F and divided by this n. This is this F is F to the force along this one. This is n is perpendicular to this Rick face. So this is a beta. So we have Fs Fn. So here is Fn. So these F and N, they are orthogonal also, okay? So these two guys are orthogonal, and so we have three the red triangles. So here is one. Also, this R is the hypotenuse, and here is another one. Also, the R is the hypotenuse, but this one, they are perpendicular also. The third triangle is FT, FC, along with this hypotenuse. We have one common hypotenuse, but this hypotenuse can be decomposed in several ways. It depends on the direction. As long as these two directions are orthogonal, so you can have this is a hypotenuse. You can just decompose it anyway, just based on your need. So here is how we calculate FC, and C stands for the cutting. So this is along is the cutting speed. So this is RFC equals. And based on this equation, so this is FC. If we have this hypotenuse, is R, the resultant force multiplied by cosine beta minus alpha. So this is total is a beta, and so here is a beta minus. This is a beta minus alpha. So this is a beta, right? So this is a beta. Here is a beta. So this is alpha, beta minus alpha. And so this is W. This W is the width of the material, the width, this direction, the thickness, and tau is the shear, and the friction coefficient equals tangent beta, and it can be expressed using these equations in terms of Ft and Fc along with the rectangle alpha. So this equation we are going to talk using these equations and to solve some problems in our this array. So this is what we have learned. And then the specific underlay, and specific underlay is the energy that is needed if we want to remove the unit volume of this material. So this specific energy have been recorded for the commonly used materials. For example, aluminum alloy, cast irons, copper alloys, and to these titanium alloys. You can see the titanium alloys we have very, very high this specific energy for material removal. The steel is a very, very big range from 247 to 1043. It depends on what kind of steel and you are quality. Right? So these are two columns. One is given in the international unit, and this one is given in the English unit. So temperature. Now this is what we have learned in last class session. So now this we learned about the temperature, and temperature is very, very important. The dependent variable that is the resultant as a result as one of the results from machining. So if you have finished the modeling using the advanced LVM, you will see the temperature increases, right? Right, everyone? Have you finished? Some students, I know some students have already finished the modeling. If you have finished modeling, when you check the results, and you will see, and when this is a tool cast the material, and the temperature will increase. So temperature is very, very important. Temperature is bad. Okay, so temperature, we know the temperature is a natural result of the cutting because this is energy dissipation there. But temperature is bad for in many ways. First one, adversely affects the strength, hardness, and wear resistance of the cutting tool. So we know all the material, no matter what kind of material you are using, as long as we elevate the temperature, and so these mechanical properties of the material will be compromised. For example, strength, hardness, and wear resistance. And this is for the cutting tool. The cutting tool, we use ceramic, we use tungsten carbide, all these materials, and their mechanical properties are compromised. Even though they are very, very tough, very good, the cutting tool materials, but still, as long as the temperature increases, the strength, hardness, and wear resistance will be bad. Right? So second one is called dimensional changes in the part, in the workpiece. We know the temperature, because the temperature will dissipate, the heat will dissipate. And not only the cutting tool's temperature will be increased, but also in the neighboring of this is the on workpiece, right? So some materials do not like heat. If there is a lot of heat, this can expand substantially as a result. And the dimensional accuracy will be bad. So in making control of dimensional accuracy difficult. So this is second adverse effect from the temperature. So the third one can induce thermal damage to the machine surface, adversely affects its properties and service life. Thermal damage. If this the workpiece in the neighborhood of this cutting area absorbs a lot of energy, a lot of heat, and what will happen? So it expands substantially. However, if this material, and so this is a heat transfer properties very, very bad, and so the energy, the heat cannot be dissipated into the neighborhood very, very quickly, what will happen? So we will have thermal damage. And so it will cause substantial, the thermal induced, this is a strain deformation, and will result in the cracks. It's very bad. The last one, the machine tool. Machine tool, when we talk about machine tool, it means that the whole machine. For example, this when we do the turning, I'm talking about lathe. When we do the milling, I'm talking about the milling machine. Okay, this is the machine tool. Machine tool itself may be subject to temperature gradients and causing the distortion of the machine and adversely affecting the dimensional control. So this is the four commonly recognized the bad effects of the temperature. And because the work done in shearing, in the shear zone, and in overcoming the friction on the ring face of the tool, the shear area is called This is the deformation, the primary deformation, primary cutting zone. So this one, the tool and chip interface is called secondary. This is a cutting zone, secondary secondary shear zone. So the main source of heat generation are the primary shear zone. Primary shear zone is along the shear plane, and the friction on the tool chip interface, and this is called the secondary shear zone. In addition, if the tool is dull or warm, that means the tool tip radius is B, it's a dull. The heat is also generated by the tool tip rubbering against the machine surface instead of cutting. You understand, everyone? So if the tool is dull, dull means that the tool tip, the radius of tool tip becomes B. Right, let me draw it. So here is my original tool. My original tool is kind of sharp, even though it has is a radius. And my tool dull means that the radius of the tool tip becomes B. Right? So this is the dull tool. Or this is a flammable wear. We are going to talk about flammable wear. A flammable wear means that this one is rubbing away. Flammable wear. This is called flammable wear. This is rubbing away. So this is your current tool. And so on and so forth. The extreme condition is that it goes this one. Right? So this is the original flammable surface. So here is your current flammable surface. This is called a flammable wear. So this is the first slide about the impact of this temperature. For temperature, people have developed some empirical equations. So here, this picture shows that the typical temperature distribution in the cutting zone. This is a cutting tool, so this is a chip, and this is a workpiece. And so here is a shear zone. So people just label this is the temperature. Okay, so this is labeled the temperature. We can see here this temperature is very, very high. This temperature is high, 700. It's the highest one because the heat will go into the chip, and then for the cutting and also the chip here, the chip and the tool will have friction, so we will have more heat. So we have these two equations. Okay, don't panic. The both equations are correct. So this equation is from the 6th edition of our textbook. So here, so this is the T0. This T0 is the depth of curve, the original depth curve. From here to here. If I expand this line, this is T0. So this is T0. For this equation, okay, for this equation, the temperature is in Kelvin. The temperature is in Kelvin, and the sigma F is the flow stress of the workpiece material as in megapascal. The cutting speed, the V is cutting speed is a meter per second, and T0 is a depth curve I just showed you. Rho C. Rho C is a volumetric specific heat of the workpiece. So it is in kilojoule per cubic meter multiplied by this is Kelvin. So this is kappa. Kappa is the thermal diffusivity ratio, which is the ratio of the thermal conductivity to the volumetric specific heat of the workpiece, and it is written in meter square per second. So this equation is for the parameters that are given in the international unit. Here is another equation. This equation is given in the 5th edition. I will not say which one is correct, which one is wrong. They both of them are correct. But this one is in the English unit, right? So for example, for this T is a degree F. If we use this equation, and your units must be this is consistent. For here, this T is a degree F because in the United States and in the UK, people use this is the degree F. You will use degree F to label the temperature. So this is the degree F. So YF here, or YF is also the flow stress, but this YF is given in PSI, right? Pound per square inch. So this is the cutting speed, the T0. T0 is given in inch. T0 given in inch, but this T0 is in meter. This T0 given in inch. And so this K, and this K is also called diffusivity. It's called diffusivity here. And I'm sorry, this should be the cover, okay? They use the cover, but and they use the K here. So this one and this one, they have the same physical meaning, also called thermal and diffusivity. And so this is rho C. Rho C, they have their own. This is the unit, but same physical meaning. So either one will be okay, but you need to take care of the units. If we use the English units, you need to use English units for all variables and then use this equation. If we use the international units, and you need to use international units for all these variables and then use this equation. Both of these two equations are correct. Right? So you can verify, okay? You can just convert for example, from English units to international units, and you get the same equation, or vice versa. So this is the temperature effect. So this here, temperature distribution in turning as a function of cutting speed. So here is the Planck surface temperature. Planck surface is here, this tool, and also here the Planck surface, right? So this is a workpiece, and this is the Planck surface. And here is the Planck surface temperature and degree. This is degree F, and so here is the distance from the two tape. Distance from the two tape. From here around this one. Suppose my tool is not one that big. So here, so along this space, but along this line, right? So this is the distance from the two tape. But here is the Planck surface. So here, this one is a local temperature at a Rick chip interface, and Rick chip interface is this area. Here also, the fraction of the two chip contact lengths measured in the direction of the chip flow. So also, it is from here, right? So this is, but here it uses a ratio now, fraction. It uses a fraction, and we can see. Here, the height temperature is usually happens at around 46 contact length. Suppose this is a tool, this is a chip. The chip. So this is a chip from here to here, and we call, and this is called a tool and chip interface. So here at this point, the chip and the tool separate from each other. And so here, and this is for this hyperscaler, and people use the fraction. So this one is gives us the option of the heat generated in cutting transferred to the tool, workpiece, and chip. So we know, and this is our tool, and this is workpiece, and this is the chip. And so this is cutting speed, and based on different cutting speed, right? The distribution of these three parts, and they are changing. For this workpiece, and for this tool. So this energy distribution. So know that most of the cutting energy is carried away by the chip. You can see the chip, the color of the chip totally different from the previous from the given raw material. Have you ever noticed that the chip is sometimes it's very dark. Sometimes we can see kind of oxide there on oxide. Also, in addition to the color, but also the microstructure changes, alteration. There is alteration of the microstructure because of the high temperature. So here people give expression, right? So this is for the mean temperature in turning on lathe. On lathe, we are familiar with the lathe. So this is temperature, and temperature is proportional and to the cutting speed. V is the cutting speed, F is the feed rate. Right? And I'm talking about the turning. And for turning, we have three different cutting parameters. One is the cutting speed. And turning, okay. This is cutting speed. And we have depth of cut, radial, which is in radial direction. And we also have this is a feed rate. Feed rate is in the longitudinal direction with respect to the workpiece, the cylinder workpiece. So A and B are constants, and these two values are dependent upon what kind of tool you are using. So V is a cutting speed, F is a feed. And sometimes it's called feed, sometimes called feed rate. Same thing, okay? And don't be confused. The F is called feed or feed rate. So here are given. And for chloride, A equals this, B equals this. For high speed steel, A equals this and B equals this. High speed steel can be used as a tool and to cut other materials. So this is just to show us the proportional relationship, but did not give us the exact relationship. And here, this is terminology in turning. This is terminology in turning. So here is a cylinder. This is this for visualization, and we just show. Actually, this is not. This is the slot. It's not that big, okay? But just for visualization purpose. So this guy is rotating this way. This is my tool. This is my tool holder. This is my tool, and here's the chip. So cutting speed is the relative speed, motion speed between your tool, which is stationary, and this is workpiece. This workpiece is rotating, right? So the cutting speed. For this case, cutting speed is going down. I'm sorry, it's going down. This is rotating, but cutting speed we can just if we just based on the diagram we see if we think that the workpiece is stationary and the tool is going on. Right? It's just a relative motion. So here is the cutting speed. So this is depth cut. Depth cut means that and how deep your tool engages and then in the radial direction. So that's the feed and feed rate means that and how fast your tool is moving longitudinally along this is a cylindrical raw material. So this is given as millimeter per revolution or inch per revolution. Okay. In one revolution, and how much your tool is moving in this direction. So knowing these three parameters is very, very important. Cutting speed, depth of cut, and feed rate. Any questions? Here is the observance. Here is the statement. The feed in turning, right? The feed in turning is equivalent to the depth of cut in the orthogonal cutting. And the depth of cut in turning is equivalent to the width of the cut in orthogonal cutting. And score this one maybe draw down. I will ask you in the middle term. So some students might ask, can you give me an example? How can we do the orthogonal cutting experimentally? Can somebody tell me how can I do that based on it? So if this one is if this material is thin walled, a hollow cylinder, it will be the orthogonal cutting. Do you agree? So why this one is different? How, in terms of what, this picture is different from the picture I showed you for orthogonal cutting. The difference is that here is in the middle. We have this one. Right? We can just imagine if we do not have this part, the whole raw material is a thin walled, a hollow cylinder. It's exactly this. You understand? I will ask you, okay? Use your own words, tell me how to experimentally use orthogonal cutting using lathe. The key word is that you use a thin walled hollow cylinder. As long as your tool's width is bigger than the wall of your cylinder, the thickness of your cylinder. Are you okay? So here is the cylinder. That is hollow. If this is hollow, here is no material. So I only have material around. This is very very thin. The space. So here is my material. Right? If I put, you just imagine. So this guy is rotating. If I just put my tool this way here. If I just put my tool this way. But this guy, the tool is not rotating. This guy is rotating. If this guy is rotating, I just put it here. This is my depth card for orthogonal, on which is a feeder in my 3D, right? And so my tool, this material will go this way. So, question.
So is it not orthogonal if the tool is like to the side?
Oh, here. This is orthogonal. It's still orthogonal.
Yeah. But if the tool was like to the side of the material,
no,
it's not
the
orthogonal.
tool is, as long as the tool's width is bigger than the thickness of the wall. Well,
So is it? It wouldn't. So the only way to dictate it as orthogonal cutting is if, in one pass, the tool takes off the entire surface layer.
yeah, we can see that. But there is no shoulder here, right? But actually here is the shoulder. We can treat this one as a shoulder.
Wait, so is that
Yeah,
not
this one
orthogonal?
shoulder.
Is that orthogonal cutting?
No, if we don't have this one, it's orthogonal cutting.
Okay, so that's not.
Yeah, this one is not orthogonal cutting, right? So also, if you want to do the orthogonal cutting, you need to have thin wall follows the cylinder. So just ask you question.
What would it be classified if the tool is bigger than the workpiece?
Yeah, the tool, your tool, the width of the tool is supposed to be bigger than the thickness of this one.
Which is not work.
Huh?
Which is not work.
This-
Rectangle.
So that is orthogonal.
No.
Otherwise, you will have a shoulder. Otherwise, that means some material your tool cannot cut. Right? This is kind of extreme case. That means this is the solid cylinder. Solid cylinder, so my tool can cut this one, but I have other material. This material here, and it serves as the shoulder for this is the tool. That means another edge of the tool and will be engaged as well. Question?
If this is an orthogonal cutting, what would we classify this type with the shoulder, like a solid tube? What kind of cutting would we classify that as?
This is not orthogonal.
Is there a name to use for this one then, where it still has a shoulder when we're cutting?
Orthogonal is idealized case. So
Okay.
this is idealized case. But actually, we don't have orthogonal. We have, this is a 3D turning. Orthogonal is just an idealized case. What I want to test you is that how can we do the experimental orthogonal cutting? Approximate, this is orthogonal cutting. And the answer is use thin walled hollow cylinder. That's the keyword, okay? If you don't give me this keyword, wrong answer. Any questions so far? Well,
Would you say you use a thin wall hollow?
thin wall, yeah, thin wall. So this one is thin, this is thickness. And this thickness is less than the width of the car. The width of the tool. So there are several techniques for measuring temperature. We have thermocouple and thermal EMF. EMF is electromotive force, and the more commonly used one is infrared radiation sensor, and to non-contact, not non-contact sensor, just use the infrared radiation and to detect the temperature. Right? So this is very, very awesome. The thermocouple is contact. This contact sensor. This is sometimes is not very, very convenient. So EMF is based on electrical motive. So because all this is if we have an electrical circuit, if something is moving, okay, in the electrical field, and we will have this is some voltage. So this is called electromotive, the force. The actually force is called force, but it actually is a voltage. Then we talk about two wear and the fatigue. And you know, if you have the experience of using this turning machine or the milling machine, you will find that after several runs, a new tool will become warm, right? So the tool wear. So this tool will have different tool wear. This is the tool, but we just look at it this way. Here is a rig face, and we call it a crater. Right? So this is a rig crater. This is a crater width or wear depth is a KT called crater wear depth on the rig face. If this one is too many of these craters and all of this one is the depth is very high, that means if depth is very high, that means the new tool is useless. It's very easy to break. You can imagine if this is very high, right? The strength of the tool is bad. And so this is called a crater wear, rig face on rig face. And here is the flank wear, and what I just drew here. And so this is my original profile, because this guy is sliding on the surface, machine surface. So this one will be gradually warm out. So this is called flank wear, and this is flank surface. So these are two important to wear mechanism. One is on the rig face, one is on the flank surface. So flank surface, and you should know that, right? And then we just look at from this perspective. So here is a rig face. So here is a nose radius. So this is a crater. So this is a flank wear, and we just look at another perspective. So this is the depth of cross line. So here's the flank wear. So flank wear is denoted as VB. Right down, right? And the flank wear is VB, and the crater wear is KT. Crater depth, another is the flank width. So here, so this is a schematic, but here is the real one. So this is a flank surface, this is a rig face, this is a flank wear. Okay, you see? Have you ever noticed this kind of phenomena? Okay. So here is also the rig face, the crater wear. So this is flank face. Here is the thermal. Here is the thermal cracking. You can see the cracks because of the extensive heat, and this is a rig face. So we can see here and BOE. I forgot BOE. Can somebody remind me what the BOE stands for? Yeah, built up edge. And built up edge is the material from the workpiece. Okay? So because some reason, so this is part of the material from the workpiece is attached on the rig face of the tool. And so here is called BOE. The flank face, this is the flank face. So the flank wear, crater wear, achieve the cutting edge, C is achieve the cutting edge. Cutting edge is some of part of the cutting edge is keep on. Question.
It's like the built-up edge having like a little bit of the material like welds to the tool or something, or
The BOE in it.
is that how does it happen?
So because the compatibility of the tool material and also the workpiece material at some temperature, and they just attached very, very closely together. Yeah, so it depends on the compatibility of these two materials. This is PUE. It's not all. It's not happening all the time. Right? So it depends on what kind of material you are using for tool and what kind of material you are using for the workpiece. The D is thermal crack. The E is a flank wear and a build-out edge. So two wear, and here is the genius. Okay, the flank wear. I talk about the flank wear, and flank wear is denoted as VB. Flank wear, which has been studied extensively, because why this one flank wear is more important. You can see why. Studying of the tool along the machine surface, right? If this flank wear is bad, and your tool is going to rubber on the machine surface. And the machine surface finish will be bad. And this causes adhesive and or abrasive wear, and depending on the material involved. And second one, temperature rise because of its adverse effect on the tool material property. So this is the flank wear. So the Taylor, and here is a genius named Taylor, and Taylor published in 1907. This more than 100 years ago. So he has done a lot of experiments, okay? And he found this equation holds. This equation holds. I need to tell you, okay? So the V is the cutting speed. He found that the cutting speed is a dominant influencing factor for the tool life. So the V is the cutting speed, and T is the tool life, N is exponent, is dependent upon your material, a tool material, and also piece material. And C is a constant. And this is here is one equation, and here is another equation. I want to clarify, okay? So both of them equations are the same. So this one is from the previous edition of the textbook, the same authors. So here is the current one, the 6th edition. So the T here use a capital T, here is a lowercase t, the same thing, right? Capital T and lowercase t, they are corresponding to the tool life, and which is written in terms of minutes. You understand, so everyone? If we use see this one equation, don't panic. If we use this equation, don't panic either. Right? The same authors, they just give us two different equations, but we can say the same. Okay, so here, this N, this range of N depends upon the cutting tool, the tool material. On different material, we have different, this is the exponent value. So, although the Taylor is a genius engineer, okay? He gave us this equation, but as the time goes, and people modify this one a little bit, also include the influence of other two the cutting parameters. And here is the cutting speed, and then we have this is feed rate and depth card, and are also included. I'm going to show you the modified equation. So we are going to use this equation to solve problem this Friday. So before I talk about modified Taylor's equation, we call the Taylor equation or Taylor method or Taylor curve, right? So here is effect of workpiece on tool life. So the cutting speed is a tool life written in minutes. So here you can see it is increasing as the cutting speed increases, the tool life decreases exponentially. So that means the cutting speed plays a very, very important role in the tool life. So A, B, C, so different materials. So this picture also shows us the skill, therefore the skill there. Okay, so this is the cutting speed. You can see the cutting speed as the cutting speed increases, and tool life is dropping, just like free body dropping. So this is not good, right? So we want, and for economy, we want to maximize the life of tool. The effect of the workpiece on tool life, and here are several observations. So first one is rapid decrease in true life as cutting speed increases. So we see that all these curves, different materials, all the curves just drop this way. Second, the strong influence of condition of workpiece material on true life. So depends on your workpiece. If your workpiece is very, very tough, definitely the true life is bad, right? It's understandable, right? You need more energy and to cut the tool material. The huge difference in true life for different microstructure of the workpiece. And still, workpiece, even though the same workpiece, nominal workpiece, but as long as the microstructure changes, material mechanical properties changes also. The heat treatment of workpiece is important largely because of increasing hardness. The harder, if the hardness is high for the material workpiece, true life is bad. The last one is impurities and hard constituents in material. Sorry, this is another one. Are important because they reduce true life by their abrasive action. Because the impurities usually are much harder than the mother material, than the major material, and harder constituents. They can just abrasive the wear. Right? I'm going to test your understanding of this. And true life curves. So here's the cutting speed, and this is true life. So different is the materials. You can see different materials here. For variety of cutting tool materials, the negative inverse of the slope of this curve is exponent of n in true life equation. For this one. So for this one, gives us relationship between measured temperature during cutting and true life. The temperature, if the temperature is high, temperature true life is low. Why? Because the higher temperature, the much easier for us for the material, for the tool material to be worn out, to be worn off either on the flat surface or on the workpiece. We know the higher temperature, the material becomes softer. So here are allowable average wear band. This is for the flank wear, right? So you should know that flank wear. So allowable. If your cutting tool VB is higher than this value, and you are required to change and then use a new tool. So for turning, base milling, annealing, drilling, and riveting, and for different cutting tool, we have different is the wear length. So this, remember, this allowable average wear length is for the flank wear. Right down there, for the flank wear. Flank wear is on the flank surface. And here are the modified here are the modified is the Taylor true life equation. So it's a C. We have velocity here, the current speed. T is the true life in meter. Eliminate. D is the depth cut. F is the feed rate. N, X, Y, and so they are determined experimentally. Right? So we can see the T can be written in terms of this one. So the T can be approximated using this equation. So here are the two observations. If the feed or the depth cut is increased, the cutting speed must be decreased, and vice versa if we want to have the same tool line. Right? The C is constant. A reduction in the cutting speed will allow an increase in feed or depth cut. So we will know that sometimes, and we still want to have the consistent tool life, but we need to lower the speed in order to have higher feed or depth of cut. Then cradle wear. Here's the cradle wear. I'm going to finish very quickly. Cradle wear on the surface. So here is the average two chip interface temperature. So here is the cradle wear rate. So you can see different temperature and different the cradle wear rate. And the higher temperature, the higher the cradle wear rate. So different materials. High speed steel. So this is the carbide, C1 carbide, and C is and C5 carbide. So this is the cradle wear. See, you can see carded this way. So this is a chip. So this is our tool. And here you can see very clearly, and this is crater, and just like the craters we saw and we see on the moon surveys, right? Big face, crater wear, is a flank face, is a chip. So the chipping, and chipping is a break of the tool material. It's used to describe the breaking away of the piece from the cutting edge of the tool. And chipping can be very small, or they may involve relatively large fragments. It depends, the cross chipping and fracture. And chipping is a phenomenon that results in the center loss of the tool material, just break. Two major causes are mechanical shock and the thermal fatigue. Mechanical shock, because this is assembly, this is a relative motion between the tool and the workpiece. And the thermal fatigue means the temperature. If the temperature increases, and the strain and will increase as a result, and we will have excessive stress. The stress can cause this is